Hello, today I'm going over measurements and uncertainty lecture. So we're just introducing the idea of measurements in science and in chemistry and how we take measurements and organize them. So I'll start off here. Measurements are essential quantities consisting of both a number and a unit that helps us navigate daily life and scientific inquiry. So number and unit, that's like 14 meters. That's the number, that's the unit. The meters is the unit. Whether we are checking the outside temperature or choosing clothing or measuring ingredients for a recipe, these values provide necessary context for our actions. In professional scientific fields, recording these measurements accurately using the International System of Units, SI, that's up here, is a fundamental requirement of experimental success. So these are some of the basic units of the International System of Units. When scientists are talking to each other about time, they're going to refer to seconds, generally speaking. When they talk about mass, they're going to be talking about grams or kilograms. So standard units with a standard abbreviation so that people can communicate those numbers accurately. Okay. In the study of chemistry, researchers frequently encounter values that are either extraordinarily large or incredibly small. So this happens all the time, and you can see examples here of some numbers as they get larger going up, where you have huge numbers of zeros followed by a 1, and then the opposite direction, they get really, really, really small. So to give you an example of stuff that's really, really small, if you're measuring the distance between two atoms in meters, that's going to be an extremely small value with lots of zeros. So you need a good way of writing this out. Writing out these numbers in standard form is cumbersome and often leads to errors due to the long string of zeros required. So if you have to write out this many 21 zeros, it's easy to leave out some. Utilizing scientific notation provides a much more efficient way to manage and communicate these extreme values without losing precision. Okay, scientific notation. Scientific notation works by expressing a number as the product of a coefficient and 10 raised to a specific power. Now that can be a little confusing, but the example makes it pretty clear. And this is not the activity where we're going over how to do scientific notation and practicing it. This is just introducing this idea. So these examples actually provide you pretty basic and good examples of what we're doing, converting one number into a shorthand form. To maintain consistency, the coefficient must be at least 1, but less than 10. So they're talking about this number here, the coefficient, followed by an exponent that indicates the decimal's movement, which we saw there. This system allows a complex value like that to be represented cleanly as this right here. Same number, smaller space. Reliable measurements are the foundation of success in both chemistry laboratories and various daily activities. Accuracy refers to how closely a specific measurement aligns with the actual or true value of the object being measured. So in this particular case, when we're talking about accuracy, we know what it should be, and the measurement should be close to that known value. Accuracy, so bullseye here, right? All 3 of the darts went to the bullseye. That is accurate. That's what they were trying to do. They wanted to get the bullseye, and all 3 hit, very accurate. Precision is a distinct concept that describes how closely a series of repeated measurements are to one Precision is a distinct concept that describes how closely a series of repeated measurements are to one concept, regardless of the true value. So precision. This one here has good precision. They're all close together, but poor accuracy. They were trying to go for the bullseye and did not get the bullseye. So poor accuracy, but they were all grouped together for good precision. To evaluate these qualities, a measured value must be compared to a known correct value for accuracy, while two or more repeated results must be compared to each other to determine precision. Okay, and then the final one shows like poor accuracy and poor precision. They did not hit the bullseye, and they didn't even get the other darts close to the same spot. Significant figures represent the total number of digits in a measurement that carry meaningful information about its precision. All right, so significant figures, well, that's something we'll come back to because this is another thing that we can practice and do practice problems on. This is just introducing the concept. In any given measurement, the final digit is an estimate while the preceding digits are known with complete certainty. Okay, let's look at this one. The 6, the final digit, is an estimate. The next one, 0, is known because we know that it's under 1. So that has to be, a less than 1, which it is, 0. That's a known. The 6 is an estimate. We don't know that that's 0.6 meters because there's no indication, but that looks about right, And that's what we're going to see in these other examples too. Reporting these figures correctly ensures that the data accurately reflects the limitations of the measuring instruments used. So now let's say I use a different ruler. Well, this one is more precise. It has more markings on it. So remember, the last one is the estimate. I can't be sure that it's a 1 right here, but it sure looks like it could be a 1. Maybe it's a 2, maybe it's a, 0.5. So that's my guess. The next one, 6, is for sure. I can see that it's past the 6 mark here, but not to the 7 mark. That's guaranteed. Same with the 0, still below 1 meter. And then it has another example where it's even more accurate or more precise. The level of precision in a measurement is directly determined by the quality and calibration of the instrument being utilized. For instance, a scale with finer markings allows for more significant figures because the estimation occurs at a smaller decimal place. They're just saying like this ruler here has more markings on it. It's more precise. Consequently, maintaining the correct number of significant figures is essential for ensuring the subsequent calculations remain scientifically valid and reliable. This will get confusing when we start doing calculations, but you just need to practice at it. Okay, I hope this helps. Thank you very much.